Well, the reason we're called tutors at Quest, all the faculty are called tutors, is because we actually teach as opposed to lecture. But unfortunately today I'm going to lecture. I gave a class in the summer for the graduate students at Columbia, which among other things tells them how to give a talk. And contrary to the advice people usually get, which is never underestimate your audience, use all those big words, make sure you throw in all the references to the right famous people, my advice is always never to overestimate your audience. And this comes about because of an incident that occurred to me about 20 years ago. The physics department at Columbia used to have its colloquia at 11 o'clock on Friday morning, and then everyone would go to the traditional Chinese lunch. And so we had a talk by an astronomer at one of these colloquia, and he was talking a lot about massive stars. And as I was walking to lunch with one of my senior colleagues at the time, a very well-known but shall remain unnamed particle physicist, he said, well, David, this guy was talking about massive stars, but you don't really know the massive stars, right? He was talking about bright stars or something. You really shouldn't call them massive. And I said, no, we actually know the massive. So how can you know the masses of stars? And I said, well, because they orbit around each other and there's these laws of motion that Newton came up with. And they go, really? You actually measure the masses of stars? So I'm going to suggest a slight emendation to the title of this meeting. Maybe it's using astronomy to teach physicists.
I was trying to be tactful.
You were trying to be tactful. So don't take offense if I'm speaking below you. But what I'm going to try to do is give you some interesting ways to introduce some of these concepts, which, if they're interesting, even if you know them, if it's an interesting new way, it's sort of worthwhile. So I always start my talks on the X-ray universe by talking about how terrible your eye is as a tool to measure the universe. I mean, your eye sees precisely 1 octave of radiation, from about 380 to about 760 nanometers. Right? The universe sends us 50 octaves of radiation, and you see 1, you see 2% of the total. And all of the telescopes built from 1610 until 1950-something only saw this 1 octave of the universe. I mean, imagine your ear hears 10 octaves of music, right? So rather than slicing off this tiny little piece of the spectrum, your ear hears at least 10 octaves of the spectrum. Imagine how terrible it would be to listen to music if your ear only heard a single octave. Well, you don't have to imagine that, because I found a clever graduate student at Columbia in the music department. And so I took the Ode to Joy, and I did to the music what your eye does to the universe. Sliced it off 1 octave at a time. So here, as a chord in the orchestra that piccolos only have the double basses, you're hearing 10 octaves of radiation. But now let me put a filter on that gives you 1 octave around the 448. I mean, from the rhythm you can sort of tell what it is, but it's not really very attractive. And then let's just take another random octave like your eye does. Right, so it's another random octave. And now, this probably won't even work with these speakers. That's another octave. Random tiny piece of this spectrum of music that you want to hear. Hard to recognize that. And here's one a few octaves higher. This would be the equivalent of the X-ray part of the spectrum. Sounds like a bunch of angry crickets, right? It's only when your ear and your brain integrate these stories whole octaves that you get the experience of the music that you're using. So, what astronomy's been about for the last 60 years has been opening up these other 49 octaves so we can see the entire variegated picture that the universe presents to us. Now in visible light, color is represented there, we see things that are at a temperature of about 5,000 degrees. That's not an accident. We grew up on a planet that revolves around a star that's about 5,000 degrees, so naturally our radiation detectors were tuned to 5,000 degrees. X-rays, of course, are much shorter wavelength, much higher energy, and X-ray light is characteristic with a black body spectrum, and you can do a peek of the spectrum and see what that is, and it comes out to about 5 million degrees. So the question naturally would be, if you've never looked at the X-ray sky before, which was the case in my lifetime, is there anything in the universe hot enough to produce X-rays? Well, so here's what the sun looks like if you have binoculars and a solar filter. It's pretty boring. What you're seeing is where the surface of the sun is not, of course, a solid surface, but what you're seeing is the surface that emits the kind of light that your eye is tuned to detect. So you're seeing a surface at 5,800 degrees, but if you put that into lambda max equals 0.0029 meters over t, is 500 nanometers, which turns out, not surprisingly, to be the peak of the sensitivity of your eye. You can also notice, though, which you can't with your naked eye, there's a few little black splotches on there. Well, so what does black mean? Black is the absence of light, right? And therefore, that means those pieces of the sun aren't emitting light, so you think, well, maybe they're a lot cooler. But it turns out, when you look at the sun with an X-ray telescope, which of course you have to go above the atmosphere to do because you would say photoelectric absorption of the atoms in the atmosphere don't allow the X-rays to penetrate to the ground, the sun looks somewhat more interesting. That's an X-ray picture of the sun. And those little black dots turn out to be the brightest places here, because this is where the gas is at 5 to 10 and even higher million degrees. And of course there are black regions of this part of the picture as well, and that's where there is no gas at temperatures of millions of degrees. And the consequence, the sun is not emitting at that. Roger can take over now. So you can see the picture is remarkably different. It's as different as the first octave I sliced out of the Ode to Joy and the second octave I sliced out of the Ode to Joy. And therefore, clearly opening these windows allows us to give a much richer picture of what the universe is like. Now, if you want to teach physical principles about this, there's also, although that's the history of the sun over 11 years, the sun, of course, varies in its activity, and the number of sunspots on its surface range from about 0, as we had a few years ago, up to as many as a couple hundred at a time, and therefore the amount of activity in these fundamentally magnetic events in which there's huge amounts of physics to talk about, some we never talk about in E&M, like magnetic reconnection, the connections of north and south poles together, which releases enormous amounts of energy, heats the plasma to high temperatures, and powers the corona of the sun, this glowing halo around it. So how do we do these things? Well, we can first of all, as I say, have to go above the atmosphere. So the first thing you can actually even put into a standard introductory physics class is rockets, right? Rockets go up and they come down. The first X-rays were detected from space by modified V2 rockets that were captured after World War II. A little piece of film put in the canister, send it up, and let it fall down. Perfect parabola, just like that, and they detected X-rays from the sun. Now we have somewhat more sophisticated ways of doing it, but nonetheless, that's some physics you can put in, and you can put in all kinds of fancy stuff about how the rocket is spinning to be spun up, to be stabilized, and then it has to de-spin again, and you can even have them calculate the probability of the instrument you worked on for 5 years as a graduate student coming down a lake or a tree or something like that, and so lots of things to do there. But of course, just putting a piece of film in a nose cone of a rocket doesn't give that spectacular picture of the sun with arcsecond resolution. So how do you make X-ray mirrors? And you might just pose that to a student. How do you make an X-ray mirror? You say, well, just make a mirror and the X-rays bounce off. Well, what is the spacing between atoms? Well, it's a few angstroms. Well, what's the wavelength of an X-ray? Well, it's a few angstroms. So what does an X-ray do? Well, what does it do when you go through your cheek at the dentist's office? Right? It goes right through. So you don't make normal incidence mirrors. You take advantage of what's called total external reflection. And in an optics class, in the first couple of years anyway, you might talk about total internal reflection when you sign something up such that the index of refraction is such that the reflection angle goes imaginary, and you get total internal reflection. And that's true for in the optical and the infrared and the ultraviolet part of the spectrum, because the vacuum has an index of refraction of n equals 1, and everything else has a higher index of refraction, so it's possible to get total internal reflection. But for solid materials in the X-ray part of the spectrum, a few kilovolts or so, then in fact, solid media can be less dense than the vacuum, and so you can get total external reflection. And we take advantage of that to make X-ray mirrors. Now the grazing angles have to be very small, and you can see how small they have to be here, and of course they're a function of the Z of the material, so silicon, copper, and platinum here. The angle of incidence for which you get total external reflection is about 0.1 to 0.3 degrees. So that's a really small angle. And a consequence of that is that the surface area of an X-ray mirror is not pi r squared, as it is for a normal incident optical mirror, but you're looking at it at an angle of 0.3 degrees, and so you may get a few hundred square centimeters out of a mirror that's half the size of this room, which makes X-ray mirrors expensive. But that's what we have NASA for. Or at least that's what we used to have NASA for. So how do you build an X-ray mirror? Well, you would need to focus things to a point if you want to do it right. And there are several geometries that are possible, and this is something else that's interesting to explore that you never see in an optics class. The one that's been used in most of the X-ray telescopes that have been launched are either this model or an approximation to this model of a paraboloid surface. So you get a thing like this that's shaped like a parabola, followed by a hyperbola, and those two focus X-rays to a point. And in the ultimate example of this, the Chandra Observatory, it focuses to a point with a spot size of less than half an arcsecond. And so you can get images that are comparable to optical images from the ground if you're willing to spend, what was it, Roger, $1 billion or something like that, on these mirrors with a total effective area of a few hundred square centimeters. Now you notice at 11 keV, those angles have to be very shallow, and as you go up in energy, the angles get shallower and shallower and shallower, so you have a real problem. If you want to take pictures of the sky and X-rays that the dentist uses on your mouth, 30 or 40 kilovolts. And in fact, the only window of the 50 octaves of the spectrum that I showed you, in which we have not had a telescope flying above the Earth or observing from the ground with true focusing optics, is the 10 to 100 kilovolt band. And Roger and I both just came from a meeting at Caltech discussing the pre-launch science that we're going to do with a satellite of this type that's going to be launched on February 3rd, if everything goes smoothly, of next year, where we're actually focusing X-rays at these very high energies. And the way we do this is very clever. There's lots of interesting physics in here, too. If you have something come in that satisfies the Bragg conditions, hits a layer of higher density material and reflects off and interferes in phase with the X-ray that bounced off the surface, you can amplify the amount of reflection. And so if we want to do this for a range of energies, we make what's called a graded mirror, where we've deposited layers of varying thicknesses going down, which reflect wavelengths as the thicknesses get smaller and smaller of higher and higher energies. And you can reflect a whole spectrum of X-rays, in our case from about 5 kilovolts to about 80 kilovolts, by changing the thickness layer of this and changing the Bragg condition and changing the constructive interference. And so you can sample a whole range of X-rays over a whole broad band by playing with the composition of the surface of the mirror. All kinds of effects that don't come into play in the normal mirrors that you get in your normal second-year optics course or play with in the lab. Now, so what do we see when we make mirrors like this? Well, we see lots of things, and lots of interesting physics comes into play. Here's a picture of the moon in X-rays. Now, you probably wouldn't think of the moon as an X-ray source, because after all, the moon's not at 5 million degrees, considerably colder than that. But the sun, as you see, produces lots of X-rays, and we know we see the moon in optical light because of the light reflected from the sun. Here's a picture of the moon. Only a piece of it's reflected is reflecting sunlight. And you can see there's a lot of X-rays from that. That's silicon, aluminum, magnesium, fluorescing as X-rays from the sun and particles from the sun hit the surface of the moon, produce X-ray fluorescence, and we get X-rays where the sun is shining on the moon. But the disturbing part of this picture when it was taken was there are also X-rays from the dark side of the moon. So what's going on there? Because there's no solar particles or X-rays in that part of the moon. And it turns out those are not from the moon. Those are a very interesting phenomenon, which are also the reason that some of the coldest things in the universe, like comets, glow brightly in X-rays. Comets are big frozen snowballs, right? And yet this is an X-ray picture of a comet. So what's going on here? And what's going on in both cases is that you have a charge exchange reaction from carbon, nitrogen, oxygen, things like that, coming from the sun, high energy particles, slamming into hydrogen atoms that are in the geocorona of the Earth, just floating around out there, having escaped from the Earth, because hydrogen, other physics think hydrogen is too light to be held by the gravitational attraction of the Earth. So hydrogen atoms are constantly leaving the Earth as water gets dissociated by lightning and things like that. And these high energy particles from the sun slam into these, steal the electron from the hydrogen atom, and then the electron cascades down and emits a bunch of X-rays. And so the dark side of the moon is not really the dark side of the moon, it's atoms 10,000 kilometers up in the Earth's atmosphere that are undergoing these charge exchange reactions with high energy solar particles. And comets, which are subliming lots of ice as they come closer and closer to the sun, provides a nice big target for all these high energy ions from the sun to undergo these charge exchange reactions, and then they glow. It's a classic example of sort of serendipity or somebody having a crazy idea. We didn't know that comets did this. It hadn't occurred to anybody. The physics is pretty obvious, but it hadn't occurred to anybody. And the German satellite Rosat about 20 years ago someone on a whim decided to look at a comet, and it's sort of like a crazy idea, because comets are frozen, right? So why would you see X-rays? And that's how this was discovered. This is another cute picture taken by the Chandra Observatory of the planet Saturn. In the upper part you have Saturn, in the bottom part you have the Sun. So Saturn, of course, is pretty cold, so it doesn't emit X-rays. But the Sun, when it has a solar flare, can produce a huge burst of X-rays. And observing Saturn 2 hours and 14 minutes after this 10-minute long solar flare, the whole disk of Saturn lit up. 2 hours and 14 minutes is the light travel time from the Sun to Saturn and back to Earth. And there you see the whole planet lighting up. And I might say, well, that's cute, but so what? Well, as we launch more and more spacecraft into farther and farther orbits from the Earth, we're interested in space weather. We're interested in space weather in general. And we can see, of course, solar flares and coronal mass ejections and all these things that happen on the side of the Sun facing us. But we can't see the other side. But the planets, Jupiter, Saturn, are often on the other side of the Sun. And so we can just monitor them and we can see what's going on the backside of the Sun as well and map the space weather in the entire solar system. Okay, that's all solar system stuff. Most of us are astronomers who go considerably beyond the solar system. So let's talk about other stars. The Sun is a very typical star in many ways, so we shouldn't be surprised to learn that other stars produce X-rays as well. And in fact, many stars, particularly early in their lives, when they're formed in regions like this, produce lots of X-rays. And this has interesting implications for the history of the Earth. It is thought that when the Sun was young, because of pictures from regions like this, it produced a lot of X-rays. Now, this is one of the iconic pictures from the Hubble Space Telescope, in that pathetic little single octave that our eyes can see. And what you see are these three huge pillars of gas, dark, not because they're not emitting light, but because they're full of small dust particles that are blocking the light from behind. And it's in these regions that we expect new generations of stars to form. These little fingers like this are a few times the size of the solar system, and they represent pieces of the gas that have started rotating sufficiently that it's spun down into a pancake and is about to form a star at the center of the retinue of planets around it. And so there's dozens, if not hundreds, of stars being formed there. But in visible light, because these little particles of dust are such that they scatter the light coming from objects that hit it, buried inside here, we can't see inside. We can't see inside with visible light. But with X-rays, we can. And so if you focus on the top of the leftmost to you, pillar there, this is an X-ray picture of that same region superposed, and you'll see at the top is this bluish, bright object glowing, which you didn't see at all in the other picture. It wasn't there at all. And that's because it's a bright, young star, which is glowing in X-rays, and the X-rays are sufficient to penetrate the dust, so you can X-ray the cloud, like you can just X-ray your key, and see what's going on inside. And the color here is not random. The colors are assigned as they are in visible light, such that the lowest energy X-rays are red and the highest energy X-rays are blue. So this blue light thing up there is very hot, whereas some of these other red ones around here, which are in regions where there's no dust obscuration, so the X-rays can come to you directly, are at somewhat lower temperature, lower energy X-ray objects. These star formation regions turn out to be a very rich source of X-ray emitters. Here we have an optical picture sort of in the red and the yellow, and then the blue are X-ray sources. You see, they're everywhere. You can't see stars underneath them in lots of these dusty regions because, again, the dust blocks the visible light, but they're all over the place. And as these star formation regions grow, as the stars turn on, they have very strong stellar winds. This is just strictly an optical picture. And they blow away this cocoon of dust out of which they form, and you end up with a cluster of stars. A dramatic X-ray picture of this taken by Chandra is here. So the background white and yellow is an optical picture, but everything in red, and now the color doesn't correspond to spectral wavelength, everything in red is an X-ray picture, and the white outline shows what we managed to map. And you can see literally there's 1,500 stars in here that are formed in this cluster, some of which you can see optically, some of which are still buried in their nascent cocoons, and so you can't see them optically, and they shine soon. You can see the big bubble there where it's blown away most of the gas. You can see all of them, whereas down here you see fewer of them, and that's because a lot of the gas is there. Sufficient gas will block the X-rays as well. So that's the beginning of stars' lives. At the ends of stars' lives, they tend to emit X-rays as well. This is the globular cluster, a very old star system, gravitationally bound, 100,000 stars or so. And most of these stars, because the cluster is old, are less than the mass of the sun. They're also old, by definition, and as a consequence, they lost a lot of their angular momentum. The angular momentum is what drives the generation of magnetic fields, which drives the solar coronal activity. And so we expect these stars not to be very bright X-ray sources. But when we look with an X-ray telescope in the core of this cluster, where the density of stars is enormous, we see, in fact, there's lots of X-ray sources, more than 100 X-ray sources in the center of this cluster. And these represent a consequence of this kind of location in the galaxy that doesn't happen anywhere else, where the stars are so close together that they have lots of gravitational interactions. That the star density is sufficiently high, while they're still extremely unlikely to actually collide head-on, they're likely to interact sufficiently that they get captured into binary systems, that you have two stars orbiting around each other, a third one comes in, steals some of the energy, and makes the binary tighter or harder, as we say, and as a consequence leads to transfer of mass from one star to another. A lot of these stars are neutron stars and white dwarfs, the remnants of normal stars, which have then been captured into orbits around ordinary stars and are stealing matter from them. As the matter falls down the gravitational potential well, it heats up, MGH, get a lot of energy out that way, and if it falls into a deep enough gravitational potential well, you can get X-rays out. The end of the life of a normal star, our sun, for example, will be when it runs out of nuclear fuel at the center, it's burned all the helium it can to carbon, doesn't have sufficient overlying pressure to squeeze the carbon tight enough to burn carbon into oxygen and neon, and as a consequence, it will undergo an unstable period where it's got nuclear burning, and so the star swells up a little bit, but that releases the pressure, and you can do all these arguments about balance of pressure and temperature, and then the nuclear reaction turns off, and so the star starts to contract again. There's no energy flowing out of the center, and gravity is still there. But then, of course, the density and temperature get high enough to turn the nuclear reaction on again, and so it expands again, and it gets into an unstable oscillating mode where it blows off dozens of rings of material every few 100,000 years or so, until it's lost maybe half its mass. So lots of interesting physics in that. But these clouds of gas are heated by the star. The star is tens of thousands of degrees, and so you expect the gas to emit visible and ultraviolet light. However, it turns out these shells, as they overtake each other, produce shock waves, lots of fluid mechanics and astrophysics. And what we see is some of these regions get heated to very high temperatures, where there are gaps in the visible light, the red picture. You see there are blue X-rays. Those are regions that have heated to millions of degrees, and you see the hot X-rays filling in where the gas has been shocked to high temperatures. The most dramatic example of the end of the life of a star, of course, occurs for massive stars, which manage to get beyond the point the sun will and can easily turn carbon into oxygen and neon, and then can turn neon into magnesium and silicon, and then can turn silicon into iron, and synthesizes all the elements. So nucleosynthesis, where did the elements come from? An obviously interesting question, which most first-year physics students haven't thought about, and an interesting way to introduce the topic of the elements. Elements, apart from hydrogen and helium and a tiny trace of lithium, all came from the stars, and they came building up in a series of nuclear reactions, starting with the fusion of hydrogen and helium, all the way up to iron, which, as you will point out to your students, is the minimum in the nuclear binding energy curve, such that it's the most stable arrangement of protons and neutrons, such that if you add another proton or a neutron to an iron-56 nucleus, then you're going to take away energy. It's going to be an endothermic reaction. And if you add another proton or neutron to an iron-56 nucleus, it's going to be an endothermic reaction. So while throughout the star's life, the gravitational force trying to crush the star has been balanced by the nuclear reactions in the center pushing energy out on the star, all of a sudden, in the final 5 days of its life, a 20 solar mass star turns a solar mass worth of silicon into a solar mass worth of iron, and then tries to make cobalt and nickel, and that of course sucks energy out of the center of the star, and in half a second the core collapses. That released a lot of gravitational energy, about 300 times the sun's 10 billion year nuclear energy source in a half a second, and a lot of energy at a given moment, at a given place in time, usually called an explosion, and so the star blows up. Now, the point is the star blows up with such violence that the typical velocities of this material flying off into the interstellar medium is 5 to 10 to even 30,000 kilometers a second. And if you calculate the temperature of a shock at 10,000 kilometers a second, it's not going to give you a lot of visible light. This is a very deep image with the Hubble Space Telescope in visible light of one of the more recent of these explosions in our galaxy, Cat A. But here's what it looks like in X-rays, a little more impressive. because most of the gas is at 5 to 20 million degrees. And again, the colors here are meaningful. The blue colors are the highest energy X-rays, the red colors are the lowest energy X-rays. You notice this sort of a shell of very high energy X-rays going around the outside, and since this is spherical, the three-dimension covering part of the front as well, whereas inside the gas is moving more slowly, as you might expect, as a shock wave accelerates down the density gradient from the center of the star to a more rarefied outer regions of the star. It turns out this outer radiation here may be for a different reason as well. But you can take pictures of this remnant in single nuclear lines of the elements. So there's the total picture. There's silicon, there's calcium, there's iron. And you can see directly the freshly synthesized material this star has produced. There's tens of thousands of times more calcium and iron in this much gas as you would find in a standard interstellar cloud, because it's all been produced inside the star and regurgitated to the interstellar medium, where it will enrich the material that forms the next generation of stars. This is pretty convincing, as you see this here. But even more convincing would be seeing freshly synthesized radioactive material that has a short half-life. And that's one thing the satellite I just mentioned, which is called NuSTAR, that launches next February, will do. It will look for lines from freshly synthesized titanium-44, which has a short half-life, generated in supernova remnants, and will die within a few thousand years. And so as a consequence, we can look through the galaxy and find all the recent explosions, and look here and measure in quantitative detail how much of this element, this isotope, is produced, and use that to feed back on models for these events. The other thing that supernovae produce are two of the more extreme forms of matter in the universe, neutron stars and black holes. And this is an optical picture of what, until about 10 years ago, I guess, was called the most studied object in astronomy, the Crabman Nebula. It's a glowing cloud of gas and dust, which in the blue regions here, and again, this is an optical photo, turns out to be highly polarized. And that's because unlike most of the optical light one sees in the universe, which comes from the thermal emission of gas at a typical temperature of thousands of degrees, all that blue light there is synchrotron radiation. There's a huge source, at this point unclear, that's generating high-energy electrons that spiral in the magnetic fields of this nebula and produce lots of synchrotron radiation. So lots of interesting physics to talk about there. We didn't know for a long time what the source of these high-energy electrons were, until someone noticed that there were two little stars at the center, and one of those little stars was a little peculiar in that it turned on and off. So here are two pictures 60 milliseconds apart, 30 milliseconds apart. No, 15 milliseconds apart. In which you see there's a star there, and a star there, and a star there, and a star there, and there's a star and there's no star. It turns on and off 30 times a second. You might say, why didn't anybody notice that? And that'll give you the opportunity to talk about the flicker fusion threshold, how your eye can pick up about 20 or 25 flashes per second until it sees continuous light, which is why you can watch movies that go by at 36 frames per second, right, with seeing its continuous light. Well, when you look at this star through a big telescope, and you can see it as a fairly bright star, it just looks like it's climbing steadily. Of course, you can use the strobe effect to make your flicker fusion threshold higher. So you can go to the 200 telescope and you can put your fingers like this, and you can move them up and down like this, until the men in little white coats come and take you away. You can actually see the star turn on and off because you strobe against the frequency of the star, which is 30 hertz. And if you looked in X-rays, it would have been obvious what was going on, because that little star, and you don't see any other stars because they're not very bright, is enormously bright, generating huge amounts of X-rays at the center of this nebula, and all of that radiation you see there. In the X-ray part of the spectrum, from 0.1 to 10 kilovolts, is synchrotron radiation. So that means we have very high energy particles. The magnetic fields here are only milligauss, and so you can do that as a homework assignment. What is the frequency you get out of, what is the energy of electrons you need to get kilovolt X-rays in a few milligauss field? And as you can see, when you superpose the X-ray image on the larger radio image, the X-ray image is much smaller. Well, why is that? So you get another homework problem. What is the lifetime of a particle of this energy in Milligauss field? And you find out the lifetime is enough to go a couple years, it's a couple light years across, but not enough to go 10 years, which is how big this is. Whereas the radio photons, which are coming from much lower energy electrons in much bigger synchrotron loops, of course live for thousands of years. And so you get this slowly expanding radio nebula embedded in the middle of which is an X-ray nebula whose size is limited by the lifetime of the electrons produced by this single neutron star at the center of the nebula. That neutron star nebula is not always so obvious. This is the remnant of a supernova that went off in the southern hemisphere, also in the last couple thousand years, because since there were no literate peoples in the southern hemisphere, we don't have any record of it. And it's really hard to tell, but right up there is one of those little white things is a neutron star, and that slight purple area, which again is the higher energy X-rays, corresponds to the synchrotron nebula in this expanding supernova remnant, where here the thermal gas clearly dominates the X-ray emission completely. The amount of particles produced, the amount of light produced by these spinning neutron stars is a strong function of their rotation rate, and their rotation rates range from, in the case of the Crab, 30 milliseconds up to a couple hundred milliseconds. A couple hundred milliseconds is whatever, 6, 7 times slower, and it goes to some power to that. The cube with 4, I can't remember, but anyway, you don't always see it. Here's the remnant of the supernova 385 AD, where again, expanding ring of relatively soft X-rays of all the material thrown out by the star, and in the center of right, the neutron star producing its little blue synchrotron nebula there. And here's a remnant that's on the other side of the galaxy, about 60,000 light years from Earth, right through the center of the galaxy, never recognized before, never seen today in optical light like the Crab, but turns out to be younger than and more energetic than, about as energetic as the Crab nebula. And again, you see the expanding shell or pieces of the emission, and in the center a neutron star that's got a magnetic field and a spin rate comparable to that of the Crab, and is producing almost as much energy. Completely invisible, visible light. We detected it first as a radio source pointing the X-ray telescope, and despite the gas and dust along line of sight, the X-rays can penetrate, and we can get a picture of it.
Is that binary, or is that just vector?
No, that's just the shape of the nebula. No, it's not. Some supernovae don't come from the core collapse of massive stars, but from the thermonuclear detonation of a white dwarf, and that's one such supernova. And as a consequence, since the star explodes completely, you don't expect a neutron star left behind, and in the center here you don't see anything. What you do see is another one of these rings of blue material around the outside, and that's because while the central stuff is this roiling mess of elements cooked up at temperatures of 5 million degrees and therefore emitting thermal X-rays, this stuff around here is a result of particles accelerated by the shock expanding into the interstellar medium in exactly the same way, and you bring your ping pong paddle and your ping pong ball as when you bounce your ping pong ball off the table and then move the paddle down quickly, the ball goes faster and faster. Well, as these shock waves move into the interstellar medium, they're compressing the magnetic field there, particles get caught, they get reflected back and forth, they accelerate faster and faster in a process called first-order Fermi acceleration, and they get up to energy sufficient, even in the weak fields here, which are probably only hundreds of microgauss, to radiate synchrotron radiation. You see that around the outside of the shell, right where the shock is, where the particles are being accelerated. So lots of E&M problems there. And this I just threw in for historical reasons because we're only a few months away from the 25th anniversary of the only supernova we've ever seen blow up nearby, and that's the supernova 1987A, which occurred on February 23rd, 1987, a date I remember because it's my wife's birthday. Actually, I remember my wife's birthday because it's the day of the supernova. So in the center there was an explosion, and the star, the red things had blown off rings of material like those other stars you saw before, but we've superposed an X-ray picture here where the innermost ring of that material has now been, just in the last few years, hit by the shock wave, expanding at about 10% the speed of light from the supernova, and as the shock plows into this ring of material, has lit it up like a series of pearls on a string there. Quite beautiful. And what we're watching here is the formation of a supernova remnant, transition from an explosion, which we saw, to one of these remnants that are typically a few thousand years old. Now, we of course exist in the blue box of the galaxy here, like you and Lincoln. The center there is New York, but anyway. So we're out in the center, and if we look in visible light, of course, we get a picture of our galaxy that looks like this because we're not outside of it. If we look towards the center of the galaxy, we just see dark clouds of gas and dust as they accumulate along the line of sight, and we can't see with visible light because the dust is impenetrable by optical photons. But it's fine with X-rays, and if we point an X-ray telescope at the center of the galaxy, it's a pretty exciting place, right to New York. Hundreds and hundreds and hundreds of individual sources, some of which are neutron stars and white dwarfs accreting from companion stars, But big glowing clouds. These big glowing clouds are interesting because we look there in radio wavelengths and we can see they're big clouds of cold neutral gas, and they're being somehow fluoresced by X-rays. But in the center of our galaxy, there's no bright source of X-rays today. But we know in the center of our galaxy there's a 3.6 million solar mass black hole. And if that eats a star, it's going to produce a lot of X-ray emission. And so what is postulated is that since these clouds are a few thousand light years from the center of the black hole, that a few thousand years ago, our black hole in our galaxy was a lot more active, as we see them in some other galaxies, producing a lot more X-rays. And what we're seeing is the echo, if you will, of those from thousands of years ago as they fluoresce these clouds. Now this panchromatic or multispectral approach gives you an opportunity to talk about putting the symphony back together again by observing the same object in X-rays in blue, in visible light in yellow, and in the infrared with a series of satellites, each optimized for one of these octaves in the spectrum, and then putting together to make a multispectral false color image where the different wavelengths correspond to different colors. You can see the global structure of this galaxy. You see there's the spiral arms, which stand out very brightly in the infrared, where there are big clouds of dust-diffused gas. And then you see along these clouds, this arm over here is particularly good, there are regions that burst out into blue, where these clouds have gotten dense enough to form one of those big clusters of stars. The stars turn on, their stellar winds go off at 1,000 kilometers a second, they blow away the gas, they shock the gas to X-ray temperatures, and you end up with bubbles of hot gas along this arm as the star formation starts to take place. So it's a way to visualize what's going on quite dramatically. And if you zoom in on one of these, here's one in the local group, you can see huge numbers of stars being formed, big bubbles being blown, and the bubbles are filled with blue, which is the X-ray gas. So the structure of the interstellar medium is such that while most of the mass resides in these dense clouds with densities of 100 to 10 million times particles per cubic centimeter, the volume of the galaxy is in hot, diffuse gas at temperatures of a couple million degrees, therefore emitting X-rays, at a density of 10 to the minus 3 particles per cubic centimeter. And the structure of the interstellar medium is revealed in these multispectral pictures. Again, looking at galaxies in different wavelengths show you different pictures. The wonderful galaxy with a visible light picture, and this dark ring of dust that shows you the plane of the galaxy where stars are forming. If you look at this an octave lower in the infrared, of course that dust at a few hundred degrees glows. So now it's the brightest thing in the galaxy. And if you look at it in X-rays, it disappears because it's not hot and it's not dense enough to block the light. And so you see all of the bright sources of X-rays all over the galaxy shining through as though that dust weren't there at all. So it dramatically illustrates how looking in different of these windows gives you a very different picture of what you see. Galaxies, of course, sometimes collide with each other. That can be fairly spectacular, as in this instance here. These are visible light photographs. And the velocities of these collisions is hundreds of kilometers a second. That allows the gas to collide and forms new generations of stars, which blows out material from the galaxy because of the amount of energy involved. And again, we see as this material leaves the galaxy, the visible light material in red, and atoms glowing, the space between is filled in by the blue light because the shock gas, even at a few hundred kilometers a second, is temperatures of millions of degrees, and the gas flows out of the galaxy as a source of X-ray emission. Also flowing out of galaxies can be jets of material as a consequence of some mechanism which some guy, Blanford, once claims he understood, but I'm not sure anybody does. When matter falls into a black hole, sometimes it gets ejected as well. So it falls in along the equator and gets ejected out the poles. And these kinds of jets actually have been seen in the optical, but they're really pretty spectacular in some galaxies in the X-ray. Here you see one that's tens of thousands of light years long emerging from the black hole at the center of this galaxy. These jets have been known for a while from radio observations. This picture here is quite a beautiful example of the global effect of this ejection of material from black holes and nuclei. In blue here you have the X-ray picture, and white obviously is the optical galaxies. And you see there's a big cluster of galaxies here. Now when we look at clusters of galaxies, you see maybe 100, maybe 1,000 galaxies of stars. Each galaxy contains 100 billion, 500 billion stars, or whatever. Really impressive amount of mass in stars. But it turns out most of the mass, like normal matter, in clusters of galaxies is in a hot 10 to 30 million degree gas that suffuses the entire cluster. could be up to 10 times as much mass in this hot gas as there is in the stars and the galaxies themselves. And that blue region is what you see there. But this galaxy at the center has a very active supermassive black hole, and it's shooting out jets of material, and what you see in red is places where there are two cavities that have been blown in this hot bubble of gas by radiosynchrotron photons that have been shot out of this galaxy over the last several million years and have evacuated parts of this cavity and pushed away the X-ray gas. These clusters can be quite spectacular, as in this famous Hubble picture here, where we see there's probably 1,000 galaxies. Every yellow blob on there is a galaxy with 50 billion to half a trillion stars. But the interesting thing about this picture is these little arcs. See these little blue arcs here? Well, these little blue arcs are a consequence of gravitational lensing of background objects by this huge collection of mass in the foreground. What you're seeing is objects that are several to 10 billion light years away being magnified and distorted by the gravitational lens of this huge amount of material here. Again, only a few percent of which is seen in all those stars that your eyes can see. Another factor of 5 or so is in the hot gas that suffuses the whole cluster. And another factor of a few is in the dark matter, which makes up the dominant component of mass in the universe. And by taking deconvolving the images of those distorted galaxies, we can make a picture of where this dark matter lies. And now the dark matter, something we don't see at any wavelength, is there in blue all over the place. And when clusters come together, we can get a really dramatic picture of the difference between normal matter and dark matter. Here's a beautiful example, what's called the bullet cluster, where we have a big white collection of galaxies over there and a smaller collection of galaxies over there. Those are two masses of galaxies that have passed through each other sometime in the last 500 million years or so. Each of those clusters of galaxies have these huge clouds of hot X-ray gas associated with them. And each of them had their huge amount of weakly interacting dark matter associated with them. Well, weakly interacting dark matter means it doesn't interact, so when the galaxies go through each other, and of course they never hit because they're spaced by such big distances, they just pass right through each other. And the dark matter follows them because it doesn't interact. But the gas, in these two huge collections, 10 to the 13, 10 to the 14 solar masses of hot gas, slams into each other, and as a consequence gets left behind. So here we have the blue is the dark matter, the white is the optical. You see the dark matter has followed the optical galaxies as they pass through each other, and yet the X-ray gas has been left in the middle, shocked by the collision of the two clusters of galaxies when they went through. Quite a dramatic demonstration of the fact that dark matter exists, that it follows the galaxies, and that it doesn't interact. We take very deep pictures of the universe. We see galaxies from local galaxies to redshifts of 6 or 10 to 12 billion years back in time. When we take the same kind of picture in X-rays, we don't see nearly as many of these objects because we don't see stars that are at temperatures of 5,000 degrees. We only see things that are at much higher energies, like supermassive black holes. So the Hubble Deep Field, when it was first observed with Chandra, when it was first launched 10 years ago, found a grand total of 1, 2, 3, 4, 5, 6 of the several thousand galaxies here. And notice there's not very little correlation. I mean, these two are pretty bright, but this guy's pretty faint. That one's really bright. It's just what their black hole is doing in the center as to whether we see them or not. Subsequent to this, we spent a lot more time with Chandra, and here's now the deepest X-ray image of the sky ever made. It doesn't look so different in the optical picture, although there are many fewer sources per square degree. Again, the colors represent the temperatures of the energies of the X-rays. And you see there's a very different universe there that doesn't match at all. So, I guess I would conclude that if you want to excite your physics students by making sure you confine them to 17th century physics for the entire first year, or maybe 19th century if you get to E&M in the first year, if you want to make sure they learn physics just like you did, and as a Columbia, for the 54th year in a row, you use Halliday and Resnick to teach them, then you show them pictures of the sun like this. But if you actually want to get them excited about physics and all the interesting careers that are possible therefrom, then you show them a picture of the sun that looks like this. Thank you.
Yes, time for some questions. We just had a full course of modern astronomy.
Why do the sunspots look dark if they're hot? Wouldn't you expect? I mean, would you expect if it's a black body that's really hot, it would still be brighter at 5,000?
Yeah, well, you're seeing different layers, right? And where the sunspots occur, you've got an eruption of magnetic fields from below the surface of the sun. And since the magnetic pressure now adds the gas pressure, that lowers the pressure there. Right? So it lowers the amount of emission you're getting from that. So it's not actually black, it's just black relative to the surrounding, it's darker relative to the surrounding region because you're getting less optical photons, but there's less gas there because the magnetic pressure is supporting part of the pressure. And they turn into these bright spots because what happens is the magnetic fields erupt through the surface, the poles then move together and they annihilate. North and south poles annihilate with each other, releasing huge amounts of energy, which heats the gas to high temperatures, which gets thrown up through the loops of magnetic fields there. And the whole complicated thing going on, we saw a talk a couple of days ago, we really don't understand it all yet. And imaging these in the 10 to 80 kilovolt range, which the satellite will do, as you see the little sunspot go around the edge, will allow you to do a vertical profile of how the X-rays are being emitted and give us a much better picture. But for our closest object, it's pretty easy to study plenty of photons. There's still a lot of mysteries about sunspots, and of course they're important because they dominate space weather. And as I say, stars are thought to be much more active when they're first formed, and evidence of that and that might well have modified the formation of the solar nebula as the Earth was formed. So there's lots of interesting implications.
It seems that usually when we see astronomy, we're thinking of Newton's laws and all these functions, but it seems like with this new X-ray view, we may have some access to studying electromagnetism using a lot of the images as motivators.
Electromagnetism here, you've got nuclear physics in nucleosynthesis, you've got atomic physics in the absorption of the atmosphere to the interaction of all these particles, lots of fluid dynamics, because all these things are dynamic and shock waves and all this other stuff. So yeah, I think there's a great richness here. Again, our eyes see one octave. It's not surprising we don't see everything that's going on. These pictures are dramatic because they are dramatic. We're looking at the violent, high-energy regions of the universe and all this other physics coming.
Jim. David, you talked about a course you teach, a GE course at Columbia, where you probably use some of this for those students. Have you thought about how you would put it into a majors course? And then, that's why we do this conference, but for major students, it's very inspiring for the introductory students. You might convert some of them.
Well, 99% of our students are not majors, and so that's why I focus my time on them, because even getting 1% of those will double the number of majors we have. It's a real positive thing. There are a few things that I've done that are relevant for majors courses, not particularly related to X-rays necessarily. I did want to teach a class for graduate students that went through all of the physics and the instrumental techniques for focusing and collecting and detecting and analyzing X-rays. And there's just lots of good physics in that we build a whole course around. The question is, how do you take little snippets of this? I think this is our goal. Little snippets of this and inject them into your resonant analytic course. And I think that's what we're here to figure out.
I hope so. I think it isn't just that we want to take snippets. I just don't think there's another way to do it.
I agree. The innate conservatism of most
that, and also to get a handle, to get a sort of physicisticize the sun. You have to do something like that.
Yeah. I wanted to ask for something very specific, and that would be gravitational lensing. Can you see a way that that could be in fact included in a, say, a first-year course, or is it just out of the question?
Well, it's without using tensor equations. You don't have to go that far. You can just use the geometry. You can just do the geometry. Where do you put the lens? How does it change the lensing? Why is the midpoint between you and the source give you the maximum effect? And then moving the lens around. I mean, people have made these wonderful plastic gravitational lenses, right? And so you can move them around, and you can also do it on a computer.
I don't know about this.
You don't know this? But, yeah. You have one of these.
You have it.
Yeah.
Yeah.
And so you can give people, a visual impression of what's going on, and then just do the simple plane geometry of how the rays are traced. And that's fine for an introductory course. I wouldn't do tensor equations.
It's not necessary to do tensor equations. In the weak field limit, there is a quite simple parallelism. It's just like doing things in a flat space with a refractive index equal to 1 minus twice the Newtonian gravitational potential over c squared. So if we just say that is the effective refractive index, it's just like doing ray tracing in flat space. That's a perfectly good equivalence, and I think that's quite appropriate for a first year course.
But this sounds like a good topic to take up in a breakout session.
And a good segue into Remnant.
One last question? Take off your glasses, you're expecting that question.
Yeah.
Okay, thank you very much.